Welcome back. Today let us start looking at the situation of steady state radial diffusion in spherical pellets. Okay. I guess you get the idea. Initially we looked at rectangular Cartesian coordinate system, a flat membrane, and then we looked at a cylindrical membrane for cylindrical coordinates, and now spherical pellets to give you an idea as to how to look at a spherical geometry system. Let me present this problem to you first, and then we will figure out ways of working this out. Problem based learning. Yeah. To improve yields of ornamental plants, certain growth factors are released from porous spherical ceramic pellets embedded in the soil near the roots in a time dependent fashion. At the surface of the pellet, the growth factor concentration in the soil is Kc0. Far from the surface, the growth factor concentration drops to 0. Develop an expression for the steady state release rate in moles per time of the growth factor from the pellet. This is a problem. Please read this as many times as you want, pause the video and read this as many times as you want to get a mental picture of what is happening here. Okay. Now, with that picture in mind, let us start solving this. So, the diffusion of the growth factor is out from the sphere equally in all directions. Okay. So, this is coming out of a spherical pellet, therefore, it is good to use spherical coordinates. So, we will consider a sphere of influence, there is a small pellet which is sending out the growth factor. There is a certain sphere of influence of the growth factor, and that sphere of influence is what we are going to consider as our system. And in our system, we are mentally going to remove the roots where the growth factor is consumed, and that is not going to be a part of the system. That complicates things, and therefore, let us mentally remove that as a part of the system. Our system does not contain the roots, it is just the sphere of influence without the roots. And now, let us do a material balance on the growth factor over the above system. We are not worried about the spherical pellet itself, we are not looking inside the spherical pellet. Something is coming out equally in all directions from the spherical pellet, and the region of influence is spherical, and the spherical region of influence is what we are going to consider here, and of course, we have mentally removed the roots where things are consumed. This is spherical geometry, we are doing a material balance, therefore, we can go to table 2.3.2-1. Hopefully, you have made a copy of that. Please do if you haven't done so, and then you could look at equation C2 for spherical coordinates in that. And that equation would be this: dou Ci dou t plus Vr dou Ci dou r plus V theta 1 by r dou Ci dou theta plus V phi 1 by r sin theta dou Ci dou phi minus, I hope you know what r theta phi are. R is the radial coordinate, and theta is the vertical angle, and phi is the other angle. Okay. These three you need to completely specify a point in a spherical coordinate system. So, r, theta and phi. Coming back to this, minus di 1 by r squared dou r squared dou Ci dou r plus 1 by r squared sin theta dou theta sin theta dou Ci dou theta plus 1 by r squared sin squared theta dou squared Ci dou phi squared equals Ri. If you are unclear about the spherical system, please go to the appendix of the book. It is given there clearly, and the way to get from the rectangular Cartesian coordinate system to the spherical coordinate system is also given there in the appendix. I think it's appendix A, you can check it out. Let us see what terms are relevant here. It's we are looking at steady state conditions for our analysis, and therefore, the first term, which is a derivative with respect to time, goes to 0. As explained in the previous class, there is no Vr, there is no V theta, there is no V phi, because there is no bulk motion or convective motion of the fluid here. Therefore, Vr is 0, V theta is 0, V phi is 0. Then Ci is not a function of theta, it has to be there has to be a symmetry in all directions. Therefore, the derivative with respect to theta of Ci is 0. Similarly, there is no variation with the phi or the phi direction, therefore, this term is also 0. And there is no reaction that is occurring here, it is just diffusing out. We have carefully removed the roots and therefore, we need not worry about any reaction that is occurring here. That is one of the reasons why we mentally removed the roots from our system. We do not have to account for this term here. Therefore, what remains is di, negative is not relevant, I mean negative anyway does not matter here. Di 1 by r squared dou r squared dou Ci dou r equals 0. And r is the only independent variable here, and therefore, we can replace the partials by the total derivative. What we get is di 1 by r squared d dr r squared dci dr equals 0. This is the equation of interest here, equation 2.4.3-1. Now, we will have to solve this differential equation. The solution to the differential equation is Ci equals a minus b by r. You could recall this from your earlier classes, or you could also see this here. You would find that this derivative equals 0, and therefore, this has to be a constant, and so on and so forth. Okay. So, Ci equals a minus b by r is the solution here. We need, of course, find a and b, which are constants, and to find out those constants, we use the boundary conditions. At r equals r, at r equals the outer at r equals the radius of the pellet that is releasing at the center, the Ci equals C0, that is the concentration at which things come out, and let us call this 2.4.3-3, and at r equals infinity, sphere of influence, it ultimately goes to 0. The growth factor concentration goes to 0. Okay. So, at the surface of the pellet, that is r equals r in our situation, the concentration of the growth factor is C0, that is given in the problem itself, and at a very large distance from the center, there is no growth factor present, and therefore, the concentration is 0. Equation 2.4.3-4. If you substitute the above boundary conditions into this, we would get C0 equals a minus b by r, and therefore, a equals and 0, and therefore, b equals minus r C0, and therefore, we get Ci equals a simple C naught r by r. Okay. Please plot this. C naught is a constant, r is a constant. The small r is the variable here. Plot a Ci versus r and see how it looks. That's quite a good exercise to do, to learn, to visualize how the variations are. We will call this 2.4.3-5. We have the concentration profile. The movement is only through diffusion, and therefore, the flux is only a diffusive flux. Therefore, the flux Ji is given as di dou Ci dou r at r equals r. We have an expression for Ci. We have just derived an expression for Ci here, simple C naught r by r. We differentiate that with respect to r, we get C naught r by r squared at r equals r, substitute r, and therefore, we get here r by r squared, and therefore, r remains here. The flux equals di C naught by r. So, this is the flux that we wanted to find, as well as the concentration profile in the sphere of influence. We will call this equation 2.4.3-6. We were asked to find the release rate, we needed the flux to find out the release rate, because we know that the rate is nothing but the flux times the area. Amount per time per area is flux. You multiply that by the area, flux by the area, then you get amount per time, which is actually the rate, and in this case the release rate. So, flux is this multiplied by the spherical area, in the sphere of influence, we get d I C naught r by r times 4 pi r squared. This is the area of the sphere that is releasing. We want the release rate, and therefore, we are multiplying by the area relevant at that point. Okay. And if you simplify this, you are going to get 4 pi d I C naught r d I, 4 pi, there is r squared, 1 r gets cancelled. So, 4 pi d I C naught r. Okay. So, that is, let us call this equation 2.4.3-7. It is always nice to number equations. Of course, as mentioned earlier, these numbers refer to the equation numbers in the textbook. So, they may not be sequential in this particular presentation, but they correspond to the equation numbers in the book, which is which makes it easier in the long run when you refer to the book. Okay. I think that solves this particular problem. We found the release rate that we needed to find. As to do this, we needed the cell concentration profile and the flux, both of which we found. Okay. So, this was an application of the material balance expression equation of continuity to a spherical coordinate system. Okay, I think we should stop here in this class and continue with other aspects when we begin the next class. See you then.